All right, let's get right into it. The entire green energy revolution, everything from the EV in your driveway to those huge grid-scale batteries, it all runs on lithium, and demand is just exploding. So to keep up, the industry is betting huge on this new technology called Direct Lithium Extraction, or DLE. It's supposed to be faster, cleaner, way more efficient, but there's a problem. A lot of these shiny, high-tech projects are crashing into a very, very low-tech wall.
So that leads to the big question that you see all over the place online. Is DLE the real deal? Is this the game changer that's going to power our future? Or is it just a giant money pit where incredible ideas go to die? We're going to break down the myth versus the gritty reality.
When you look at it on paper, DLE seems like the perfect solution. It's pitched as this almost magical process that can fix the world's lithium shortage, do it with incredible speed and efficiency, and, have a much smaller environmental footprint. What's not to love? To get what a huge leap this is, you gotta look at the old way. The traditional method is just unbelievably slow. You pump salty brine into these massive ponds and just wait for up to 18 months for the sun to do its thing. DLE completely flips that on its head. It's an active, chemical process that pulls the lithium out in a matter of hours. We're not talking about a small improvement here. This is a total revolution in speed. And it isn't just about going faster, it's about being smarter. With those old evaporation ponds, you lose a ton of lithium. Recovery rates can be as low as 40%. DLE can get that number up to 90% or even higher. Think about that for a second. You're getting almost double the product from the exact same resource. That is a massive, massive jump in efficiency. So the chemistry is brilliant. It's faster, you get way more product, it's better for the environment. It sounds absolutely perfect, right? But this is the pivot point. This is where the clean, elegant, high-tech idea that was cooked up in a lab smacks headfirst into the brutal, unforgiving reality of industrial-scale physics. And that collision? It happens in a place that people in the industry have a grim name for. They call it the Valley of Death. It's this notorious gap where so many promising, heavily funded technologies end up when they try to make that jump from a small pilot project to a full-blown commercial operation. And here's the crucial thing to understand about the Valley of Death. It's not usually the core chemistry that fails. The science often works perfectly. The failure comes from something way more mundane. The pumps, the pipes, the tanks, the basic plumbing of the plant literally can't survive the process. So to really get why, we need to introduce the two main villains that are bringing these multi-million-dollar projects to their knees. We're talking about a nasty 1-2 punch of physical destruction and all-out chemical attack. Okay, first up is something called liquid sandpaper. This happens in hard rock mining, where the lithium is locked inside a mineral called spodumene. You grind this rock up, mix it with water to make a slurry you can pump, and, well, you've basically just created a liquid grinding paste that chews up your equipment from the inside out. And I'm not exaggerating here. Spodumene has a hardness of 7 on the Mohs scale. To put that in perspective, that's the exact same hardness as quartz. So just imagine pumping liquid quartz through your pipes 24/7. It is incredibly destructive, and it goes right for the weakest points in a pump, like the mechanical seals.
The second villain is what you can only really describe as chemical warfare. These DLE brines, especially the ones from geothermal sources, are one of the most hostile industrial environments you can imagine. They're hypersaline, they're packed with corrosive chlorides, we're talking over 100,000 parts per million, they're hot, and they're often treated with seriously powerful acids.
This chemical cocktail is absolutely lethal to standard industrial materials. You take something like 316 stainless steel, the stuff we think of as tough and corrosion resistant. Well, in a hot, high chloride DLE brine, it fails. And it fails catastrophically through a process called stress corrosion cracking. The material literally just falls apart in a matter of months. So, you've got your equipment being shredded from the inside and literally dissolved from the outside. What does that actually mean for the bottom line? Well, this is where the technical problems start a massive financial bleed. A single broken part isn't just a maintenance headache. It's the beginning of a cost spiral that can kill a project. Let's just put a price tag on this, shall we? According to the data, just one single hour of unplanned downtime at a big lithium facility can cost the company over $100,000. 1 hour. Now imagine that happening every single week because a pump seal keeps failing. The costs just become astronomical. And that one failure kicks off this devastating domino effect. It starts with lost revenue from the downtime, sure, but a leak of corrosive brine or acid isn't just a mess, it's an environmental violation that can lead to massive fines from regulators and could even force a complete plant shutdown. This is exactly how these projects stumble and fall into the valley of death. So, how do you get across that valley? How do you actually make these projects work? Well, it turns out the answer isn't about finding a slightly better part. The real solution is a totally different way of thinking. It's about forging a kind of industrial armor for the entire system. And that brings us to the real twist in this whole story. The key insight that's saving these projects is that the solution isn't better chemistry, it's better plumbing. It's all about smart, robust systems engineering, taking old proven principles and using them to design the whole network of pumps, pipes, and tanks to survive this brutal environment right from day one. Building this industrial armor really comes down to 3 basic rules. First, you get rid of the weakest link, the mechanical seal. By using sealless pump designs from the very start, you take away the one part that liquid sandpaper loves to destroy. Second, you choose materials that are chemically immune. You stop using standard steel that you know is going to fail and instead use advanced plastics that just don't care about the corrosive brine. And third, you engineer for total containment. Using things like double-wall tanks means that even if something does fail, a small leak can never become a catastrophic environmental spill. And when you take this engineering-first approach, the impact is just staggering. A 55% reduction in the total cost of ownership, that's not a small saving. That can be the difference between a profitable plant and a total failure. And a 90% drop in downtime, that means the process just flows almost all the time. These aren't just little improvements, they are what actually makes DLE commercially viable. So, why do all these nitty-gritty details about pumps and plastics actually matter? Because when you strip away all the complex geology, the financing, and the brilliant chemistry, it all comes down to something incredibly simple. For these billion-dollar projects, the ultimate value is, and this is a great quote from the source material, the certainty that the process will flow. Without that certainty, you really have nothing. So in the end, the future of the green energy revolution doesn't just hinge on brilliant chemists in a lab. It really depends on the unglamorous but absolutely critical work of engineers building systems that can actually survive the fight. The energy revolution is here. The real question is its plumbing ready for it?